All right, get your books open, please, here to page, let's start on page 138, 139, and the solving equation packet. I've still got the solutions somewhere. To that packet. Or do I? Did somebody that was here this morning steal mine? Never mind. All right. So we will not spend a great deal of time on these, but there are a few things I would want to talk about. And so if you want to come in at a later time, on your own and ask about some of these, or to go back and check any that you didn't maybe get to, because they're all worked out here and everything. And most of them are right. I think I made, looks like one mistake.
Which one was that?
On the trig equation one. Someone was kind enough to point that out to me. I appreciate that.
Which one?
So, anything on, I want to make one comment on the website. I put up some videos that are some ones I've done in previous years. Global max min. Without a calculator, that's the list of candidates, okay? So I think that was number 24 in the book that I did in class one day. So there's probably 2 videos of that, whatever day we did that, probably the 29th. But then it's just, here's a video that instead of the whole class period is just number 24, that global max problem worked out. So if you want to revisit that. And then the local max min problem, I think it was number 20. And I've got that one worked out. And then we're getting into the trig ones. So I've got a trig local max min, no calculator, and a trig inflection point problem, no calculator, worked out there. I think this one might be like number 37, part of, we worked out in class the other day with the local max min. So that might be that one. And then this IVP, initial value problem, that's something we're going to learn about today. Okay, so I've got some additional ones on there. All right, so anything on the first page, any comments on the first page of the equation packet? Because you know what, the reason you need to solve these equations obviously is when we're doing max min, inflection point, any of those chart kind of problems, that global max min, they all start pretty much, do the derivative or maybe a second derivative and set it equal to 0. And then you have to solve it. So you've got to be able to solve equations. All right? So anything on the front page? Second page. Number 21, I did intend to be solved with the calculator. So I did not point that out there, but that was a calculator solve. Okay. So those of you that were able to just know that answer by looking at it, good. That's good. All right. How about the last page? 15. Yes, on 15, any time we have exponents that are variables. Is that the one you're talking about with the whoops?
Next page.
Okay, 15 right here. So anytime we have exponents that have the x in them, and that includes when it's on both sides, what I think is the best option to do is take the log of both sides. Matter of fact, this is one of the reasons when we were doing problems back in Appendix E, the first week of class, we were solving problems like e to the 3x equals 8, and we had to solve this. And what some of you did is you just did this you put this into log form. You said, okay, this will be log base e of 8 equals 3x, and you just go from there. What I had suggested was do the log of both sides. Now, that actually makes it seem like a little longer problem, but then you realize that one of the rules of exponents in logs is you can bring this power down in front, you get 3x ln e equals ln 8, and then what's ln e? Ln e is 1. And so you end up with 3x equals ln 8. Now, it seemed like a little more work, So if you can notice that exponential form, that's fine. The advantage to doing log of both sides is now when you get a problem with x's in both exponents, that exponential form thing doesn't work nearly as well. Okay, it still can work, but here then you're better off just doing log of both sides. So you get this equals this. We can use that property of logs where we can bring down the x minus 1. Now you really have to be careful with your parentheses here, and then we bring down the 2x, and of course ln e is just 1, so that's just going to be 2x right there. Now, and this is something, this is an algebraic technique that we will run into many, many times throughout the course of the no calculator problems that we get into. ln 5 is just a number. Since it's no calculator, we don't really know its decimal equivalent, we don't care. But we have to treat it as if it was a 7. It's just a number. And if there was a 7 sitting right here, what would you do right now? You would divide by x minus 1 if we're trying to get the x by itself? I would say you'd probably distribute, wouldn't you? So if that was a 7 sitting right here, you'd distribute. So that's what I'm going to do. So I'm going to take the ln 5 times x, and we usually write it this way. If it was a 7, of course, we'd write 7x. But when it's this, and the reason we do that is some of you are not quite in the habit of putting parentheses around the 5 when you do your ln. And so then if you write ln 5 times x, now what is that? Is that ln of 5x? Or is that ln 5 times x? Those are two totally different things. So to avoid that, you're better off doing this. Matter of fact, I think the best thing to do is to get in the habit of putting parentheses around the argument of a function. Same with sine. When you write sine x, we should put parentheses around it. Okay? So x times ln 5 minus 1 times ln 5 equals 2x. Now what we need to do is get the x's on one side, right? Isn't that what you learned in Algebra 1? Get the x's on one side. So I'm going to bring the 2x over here, and I'm going to add the ln 5 over to this side, because ln 5 is just a number. So get that over there, get the x's on one side. Now, what can I do on the left side now? I can take out an x. Okay, so what I did there was gather my x terms together on one side. All right, now I take out an x, because to be honest, that's what you do. When you have 3x plus 4x, we never do it this way, but what's 3x plus 4x? 7x. Well, why is that 7x? It's because you take out an x, right? You factor out an x, and 3 plus 4 is 7. That's why 3x plus 4x makes 7x. Okay, well, that's what I did right there. I took out an x. Now we then divide by that amount. So I get x equals ln 5 over ln 5 subtract 2, and no, you can't cancel the ln 5s. Okay, and that is the answer you want right there. Okay, and you can try that one. You can do a solve on your calculator, test it. I think it gives you that same answer when you try it. That is a technique we will use a lot. Not only the log of both sides, but also this idea of gathering the x terms on one side. If we're trying to solve for x, gather the x terms on one side so you can factor out. All right. Anything on the last page? I do know, or not the last page, but the trig page, about maybe number 4 a little bit. Now, maybe you saw all the answers. Maybe you saw the answer sheet and you're good with what you saw there. But what was the trick? What was the necessary thing to do on number 4? What was? I had to change the cosine into sine. I had to get these to be the same. And so what I did is I substituted, and this is, of all of the trig identities you really need to know, that's one of them. You need to know cosine squared plus sine squared equals 1. And so that means cosine squared is equal to 1 minus sine squared. Okay? So all I did was make a substitution right there. Okay? I substituted cosine squared for 1 minus sine squared. Now when I distribute the 2, I'm going to get 2 minus 2 sine squared plus sine equals 2. Nice thing is when I subtract the 2's, they disappear. So now I can take out a sine, and I get negative 2. That's a square there. So I get negative 2 sine plus 1 equals 0. And then either one of those would equal 0. So either sine is 0 or sine is I think 1/2. So this would be pi 6 and what, 5 pi 6 for sine. And then where does sine equal 0? That'd be at 0 and at pi and at 2 pi. So, right, and we talked the other day about drawing the triangles and all that. And again, I've got that on video with the triangles. I've also got a video, if you remember, there's another video up online that says trig review, just the trig review stuff we went to. So again, if you feel like you need that, go to that. Or come in and see me. Come in and see me and we can review that trig stuff. Let's talk about a couple of the calculator is especially important. And this is another big deal. Sine squared, this is our lazy notation. It's fine to use, but it can get us in real trouble. And it can get us in trouble when we're doing our derivatives here as we learn about doing derivative rules. Sine squared means sine of x quantity squared. That's what it means. You cannot type this into your calculator. Some of you have probably already tried. It does not accept that, I don't believe. It's got to be this. Now, I'm not sure if these parentheses are necessary.
You don't need to. If you type it in,
are we okay with the other one?
If you type it in without, it'll automatically stick them in.
It puts them in, so if you do that. Okay, so I was always a little nervous about this one. Is it squaring the x or is it squaring the whole thing? We want it to square the whole thing. Okay, and so I think maybe we can put it this way. Okay, now that's a lot different than having the squared inside on the x, right? That's a whole different function. So sine squared, we write it this way, that's fine, but when we use our calculator, or even when we learn some things later on where we're not using the calculator, we have to think of it like this. All right, so let's put number 6 here into our calculator. Let's just all do this together. So, so let's get a calculator window up here. We're going to go to our menu. We're going to go to solve. Okay, now all right, now it's totally up to you if you want to do any algebra to it, to simplify it before you type it in your calculator, that's fine. Or if you just want to type it the way it looks, that's fine too. I'll just go ahead and type it the way it looks. So I've got and parentheses are the thing you really have to be careful to keep track of here. Okay, so I've got a 7. I want a left parenthesis. I want a 1 minus. Okay, now, Jacob, we'll trust you here. You said that I can just put the cosine of x,
And then
go outside that parenthesis, and then square it. Okay, so that's 1 minus cosine squared. Now we got to be careful. This last parenthesis is the end of my solve. Okay, so I want to stay inside that.
equals.
So am I good? So now I needed my equals.
4 sine.
And then 4 sine x.
Plus 1.
And I have to go outside the parenthesis. Plus 1. Okay, then I have to say comma x. I've got to tell it what I'm solving for. And then I'm going to close that right parenthesis on the solve. Or just arrow past it. All right, now. This is something to really keep in mind with trig solving. When I just hit enter now, okay, you start getting this 2n pi stuff. Anytime you see that, what should come to mind is, okay, sine and cosine have infinite solutions, right? And you remember this from trig last year. Where does sine equal 1? Well, at pi halves and at 3 pi halves, and every 2 pi, it'll keep repeating those values. So you tack on a plus 2 pi n. That's what this is doing. Okay? Well, we don't want that because the directions told us to only look from 0 to 2 pi. And usually that'll be the case. Usually we're only looking in a set domain. So I want to arrow back up there and grab that thing. And you'll forget from time to time. But here's where we want to use the vertical bar. And we want to restrict the domain. And we use this a lot when we're solving with sine. But you have to go outside the parenthesis. This is the most common mistake people make, is they put the vertical bar inside the solve. It's got to come outside the solve. So we go in here, the vertical bar is right here, control equal sign, vertical bar, and then you can go 0. And we want to go back to that same menu and do less than or equal to x, back to that same menu, less than or equal to 2 pi.
Bottom left.
All right? Now, when you hit enter on many problems, it's going to try to give you an exact answer. And usually those are a mess. Usually we don't want them. Now, if it was going to come out 3 pi halves or 3 pi fourths or something like that, well, to be honest, we wouldn't be using a calculator. Those would be our no calculator problems. Generally, they come out to something messy. Now, this cosine negative 1 means what? What's that cosine negative 1? Inverse cosine or arc cosine. Okay, something we'll be talking about here a little later. But that, I don't want that. When you see that, you say, oh, I should have hit control equals. So hit, or control enter. So hit control enter and then you get your decimals. So on those last 4 questions, it was perfectly proper for you to just have answers written down. When you have one of the things we're allowed to let the calculator do is solve an equation. When we're showing our work, we need to have the equation on our paper. But if it's a calculator problem, we have the equation on our paper, we can let the calculator just get those answers. So maybe those are stationary points. Or maybe those are possible inflection points, right? That we've just solved for. All right, so then you have to scroll, you have to arrow back up there, and then you have to scroll across to see them all. And there's like 4 of them, I think. Okay, for that particular. And always give your decimal answers to 3 places. All right? So this is going to be important on this next quiz that we take because you're going to have some local max, local min, global max, global min kind of problems. And you're going to have one for sure on the no calculator. You're going to have one for sure on the calculator. Right? And it might be a trig one. It might be a trig one on both parts of the quiz. Okay? And so you got to be able to do them with the calculator, and then of course we have to be able to do them without the calculator. Same with the exponentials. All right. Let's go take a look at the homework next from the other day. Let's turn to page 139. All right, so this would be your homework where we had 6 and 8 and 16 through 30 even. Number 35, I think, on this page. All right. Now, we've got a lot to go over. I think I have a sense of where the questions may lie. And so if there are some other ones, we can see if we'll have time for those. But I think I've got a pretty good idea of some things we need to discuss. I'm going to start with number 6. Okay, number 6 says h of x equals log base 10 of x. Am I on the right problem? This is one we had, right? Okay. Now, you're supposed to find h prime of 1/10. You're supposed to find h prime of 1. You're supposed to find h prime of 10, so forth, so on. Well, before you can find h prime of 10, you need what? H prime of x, right? Before you can find h prime of 10, you've got to find h prime of x. So that's what they meant by theorem 12. Normally we won't say use theorem 12. We'll just say find h prime of 10. Okay? Well, so what, according to the rule the other day, is the derivative of this? 1 over x.
Times 1 over ln a.
1 over ln 10. Right? Whatever the base is. That was the rule. Okay? For what the derivative is for log of a base.
You can just write that as 1 over x ln of 10. Right?
That's right.
Okay.
And that's a great point. This could be written as simply this. Why would I make the effort to do that? There are some reasons why I write it a certain way. As you'll see as we get into the derivatives, how you write them goes a long ways towards understanding how to work with them. All right, but that is exactly right. So h prime of 1/10 then, for example, we would put a 1/10. Well, what happens if you have a 1/10 down there? Ends up being on top, and so we get 10 over ln 10. Now, we want to simplify these as best we can, okay? If you would have just stuck a 1/10 down there and left it down there, depending, you know, that might have been good enough. You know, if that's all you can think to do and you're not sure how it would simplify, then by all means do that. You know, it certainly would be some partial credit. If we had this problem, you'd get some points for getting the right derivative written on your paper. You know, and if you just stuck a 1/10 there and didn't simplify it, you know, maybe that would be enough. Okay, but you should go ahead and try to simplify. And then, of course, all the rest of them that you plug in there. All right, number 8's very much the same thing with that rule. Okay, the rule on number 8, g of x equals 10 to the x. The rule for the derivative of that is what? 10 to the x times ln 10. Any exponential function is its own derivative, and then we tack on that extra whatever multiplier. On a log, it's 1 over x, and we tack on, again, that extra multiplier. All right, so then you go ahead and you plug in your 1 or your 2 or whatever else they wanted you to do. Okay, so if you put a g prime of, what was 1? Negative 2 would be 10 to the negative 2 times ln 10. Now, I'm fine with that right there. You don't need to drop that 10 to the bottom or anything. That's fine. Okay? All right, next thing I want to look at is that next section of those derivatives. On 16, there was kind of a method to their madness here on how they wrote these, the kind of functions. Now, I'll be honest, we rarely will get or deal with functions that look like a lot of these did here, but they're really making you think about the rules. E to the x plus x to the e plus e. All right? So we were supposed to do f prime. Well, okay, what's the derivative of e to the x? E to the x. How about x to the e? E times x. Again, remember what I was saying earlier about ln 5 is just a number? E is just a number, 2.71. So x raised to 2.71 is a power rule. Plus, what's the derivative of e? What's the derivative of e? 0. Why? It's a number. E is a number. If there was a 7 sitting there, the derivative of 7 is 0. The derivative of any constant is 0. So it's 0. You don't have to write it. But again, people want to put e because they're thinking e to the x. That's different. E to the x is a function with e in the base. E is just a number. And, or some people want to put 1 because they're thinking, well, the derivative of x is 1, but x is the variable. See, you're doing the derivative with respect to x. X is a variable. E is not a variable. E is a constant. It's a number. Okay, so that's important to understand. All right? Then when you do f double prime, derivative of e to the x is e to the x. What number was that then? Number 20 or something? Or 24 or 22? Okay, then on number 22, we're supposed to do the second derivative. So the derivative of that's e to the x. What's the derivative of that? Now, I maybe haven't made a big enough deal about this, but when you have a number setting in front of a function, what do we do with it? It just hangs out there. Like if I had 7x squared, the 7 just stays there. You bring down the 2, times it with the 7, right? So when you have a number in front, a constant, remember what we said that did is we said that would stretch the graph. If you have a number in front, multiplied, it stretches a graph. Well, it stretches it by a factor of, in this case, e. So it's going to make all the slopes multiplied by e as well. So a number in front just kind of hangs out there. Then what do we do with this?
Bring it down.
We bring the power down and multiply it there, right? And then this would be x to the
E minus 2.
e minus 2. And of course the is already gone. Okay, now you could distribute that through if you want, but it's not necessary. You could just leave it just like that. Okay? All right. Finally, on the next one, this would be what, 28? 28, then you have to do the antiderivative of the original, right? So now we're going backwards. So we want to do the antiderivative of e to the x is, that's a nice one, right? That's an easy one. It's its own derivative, it's its own antiderivative. What about this one? Ooh. We raise the power up one, divide by that new power. Or we could, out in front, put a 1 over e plus 1, right? You divide by 2 is the same as multiply by a half. So you divide by e plus 1 is the same as multiply by a 1 over e plus 1. Okay, plus, what's the derivative, antiderivative of e? Let's think of it as a 7 again. What's the antiderivative of 7? 7x, right? 7x. Because, why? Because the derivative of 7x is 7, right? So this is just a number, like a 7. So the antiderivative is e times x. Not e to the x, but e times x. And then what else do we always need on antiderivative? Plus c. Okay? The antiderivative of a number is that number times x, or whatever your input variable is. T. Sometimes we use t as input variable. Okay? All right. And you could say, and you could think of a 0 there. What's the antiderivative of 0? Just a number, right? That's why the plus c is there. Because the derivative of a number is 0. All right, so that gives you kind of a sense of those. Now, let's look at 8. 18 says 2 times 3 to the x minus 1. All right, now, again, the 2 in front is a constant. It just hangs out there. So, and this was f. Okay, so this is f of x. So f prime of x, the 2 would just hang out there, and we're doing the derivative of this. Well, what's the derivative of, what's that minus 1 do? This doesn't, what's a minus 1 do here? That's a shift to the right. Remember that? We were talking about you got a minus 1 on the inside. That's a shift to the right. Does that affect the slopes? No, other than shift them to the right. In other words, the inside is not going to change. We do not bring the x minus 1 down, right? This is that rule. We just did one with 10 to the x, right? What was the derivative of 10 to the x? 10 to the x times natural log of 10, right? The rule, if we need to write it again, the rule was the derivative of a to the x is a to the x times ln a. That's the rule. So that's what we have here. So this is, so it's its own derivative. That's the thing about exponential, like e to the x. It's its own derivative. The minus 1 stays in there times natural log of 3. That's what the rule says, that we got to tack on the natural log of 3. The 2 just hangs out there because that's what we've always done when we have a constant multiplied out in front. It just hangs out there. Okay? Now, that was number what? 24? Or no, that was 18. 24 then is the second derivative. Okay? Now, look. The function is just that part. The 2 and the ln3, what's ln3? Just a number, just like the 2. So you got, what you have is a 2, and probably if I was going to write this, I could have put the ln3 out in front and written this as 2 ln3 times 3 to the x minus 1, right? So the 2 ln3 is just a number out in front. It's just going to hang out there. So when I do the derivative, the 2 ln3 stays there. Now I'm doing the derivative of that. Well, we already know that. Is what? 3 to the x minus 1 times an ln3 tacked on. Now, you can make that ln3 quantity squared if you want, or just leave it. Doesn't matter. Okay? So again, understand that ln3 is just a number. Just like the 2. All right, then we get to number what, 30? We're supposed to do the antiderivative of the original. Okay? Well, again, the 2 is just going to be hanging out there. That doesn't, we don't do anything with that. When you're multiplying a 2 out there, or any number out there, that's just there. So we want the antiderivative of that. Well, remember, an exponential is its own derivative, except for we got to tack this on, right? So you might think, and this is where that guess and check piece comes in. So you might be tempted to think, well, maybe the derivative was just that, or the antiderivative. Well, how do we check? Well, we go ahead and do the derivative. Well, let's see, if we did the derivative of this, would we get this? No, because there needs to be what? There needed to be an ln3 there, right, when we do the derivative. It's not there. So what could this have had that when we tack on the ln3, it made it go away? How about a 1 over ln3? And that is actually how you think through these antiderivatives. You think, well, let's see, what must have been there? Usually a constant. What constant must have been there so when I did the derivative, it may be canceled or something like that. So now let's think about this a minute. So, and then of course we got the plus c. So if I was to do the derivative of this to check, we'd say, well, the 2, that's just a number. It's just going to hang out. What about 1 over ln3? Just a number. So that's just going to hang out. So all we're going to do is this derivative. Well, what would we do? So this and this would be hanging out. So we'd have 2 and this. And like Tyler said earlier, I could make that 2 over ln3. But so I got this and this. And then when I do the derivative of this, I'll get 3 to the x minus 1. And then I got to remember to tack on an ln3. And sure enough, those would have canceled. And I'd ended up with what I needed. And that kind of makes sense. You'd think, well, the derivative rule says you got to tack on an ln(a). So maybe the antiderivative, since it's going to reverse, would mean you divide by an ln(a). And that's really what we did there. Okay? All right. Let me make one other comment because this happens all the time in the early stages of doing derivatives. If I have f as ln x, what's f prime? What's f prime? If f is ln x, what's f prime?
1 over x.
1 over x. That was a rule we learned the other day, right? Okay? What if on the quiz I ask you for the derivative of ln4?
1 over 4.
Of course it's got to be 1/4. Wrong. What's ln4? ln4 is a number, not a function. We're doing the derivative with respect to x. That's that. ln4 is like a 7. What's the derivative of 7? 0. The derivative of ln4 is 0. Okay, be very careful about that. There's a big difference between these two things here. Okay, when it comes to derivatives. So the derivative is not ln4. Or excuse me, 1 over 4. All right. Okay, let's turn to page 147. And let's look at 10 through 13. So we're going to get some more practice with the derivative rules. They're going to be relatively, the next quiz will have some of these, do a derivative, maybe do a simple antiderivative. They're relatively simple, maybe a few like the ones in there, but those got pretty tricky. Those were not just real basic ones. And the sine and cosine, we haven't, let's see, we'll talk about those here in a minute. All right, so let's go, I guess while we're on it, let's look at 18 through 34 even. And you didn't get a chance to look on your, in the back of the book, obviously, because they're even, but you did have your calculator where you could check the derivatives. So why don't you go ahead and get your calculators out right now. The direction said something about plotting a graph, and hopefully you remembered I said the other day that you didn't, we weren't going to draw the graphs of those when we did number 37 there. We talked about, because we got our calculators where we can sketch those. But if you did, that's fine. But let's take a look at number 20. All right? It says that f of x equals cosine 2x. And I think we might have mentioned this the other day. Go ahead and type that into your calculator. Remember where the derivative template is? Go over here to the templates. The derivative one is this one right here. Okay, second row. Second from the end. The one next to it with the 2 there is second derivative. Okay, this is that Leibniz notation. So we choose that. Oops, why didn't it? Oh, I wasn't down here. Okay. So we put in an x. And why is that so slow? And we put in cosine of 2x. And what, of course, is the derivative of cosine? No?
Negative sign.
Negative sign, right? The derivative of cosine is negative sign. That was a rule we put up the other day. So when we hit enter, we're not surprised to see negative sign, but we might be, and we shouldn't be surprised to see the 2 on the inside, right? Because the 2 on the inside is going to squeeze those slopes down, squeeze that graph down so all the slopes will be in different places, right? But why the 2 on the outside? The 2 on the inside, listen, the 2 on the inside, when you squeeze the graph of sine or cosine, now instead of that peak being at pi, for example, it might be at pi halves because it's been squeezed in by a factor of 2. So all those slopes, like where the slope is 0, the peak is not going to be where it used to be. It'll be at a new x value. It'll be squeezed in. So your derivative has to squeeze in just like the original. Okay? But what else happens in the slopes when you squeeze the graph? Does it make sense? It gets steeper? Right? If you squeeze that sine graph and it still only goes from 1 to -1 and you squeeze it, they're going to get steeper by a factor of 2. So you need the output of the slope function to also multiply by a 2. So whenever we have, so the rule here from now on, and this doesn't matter if this is cosine or sine or whatever, when you multiply by a number on the inside, do the normal derivative rule, but you have to kick out whatever that multiplier is to the outside also. Okay? And you can see it right there on that one. So let me give you an example of that. If I gave you the function e to the 4x and wanted the derivative of that, and we can test it here if you want to test on your calculator, but what should it be? It should be 4e to the 4x, and that's exactly what the calculator will tell you. Okay, because that 4 on the inside compressed the graph, which made the slopes 4 times as much, but it also compressed where they were. So the 4 on the inside stays, and that's a rule you'll hear me say a lot. Leave the inside alone. When you do the derivative, leave the inside alone. Do the rule, leave the inside alone, but sometimes we have to kick out that multiplier that's on the inside. Not sometimes, always. Okay, that multiplier that's on the inside. So, that's a rule. Matter of fact, if you want to put that rule in your notes, it would look like this. That rule would say if you have a function and you have a multiplier on the inside, for any function, you have a multiplier on the inside, then the derivative of that is going to be the derivative, the normal derivative rule. Okay? That's going to be the normal derivative. The inside will stay the same, but you'll have to tack on a times a. Okay, and that's true of any function, a natural log, okay, an exponential, a sine, a cosine, any of those. All right, so that was number 20. So what would have been number 26? Would have been the second derivative. So what would you get? What would you get here then if we do the derivative again? the negative 2 is just going to hang out, right? I'm not going to write it yet because I know what's coming. What's the derivative of sine? Cosine. The 2x inside will stay the same, and what else will happen? You have to kick out another 2. So you'll end up with negative 4 cosine 2x. It'll still be negative because that's just a number also. That's just part of the number. So the number stays here, right? It just hangs out. We do the derivative of sine, which is cosine. We leave the inside alone. And we got to kick out that 2 that's on the inside, which ends up with a 4. Okay, and then number, what was it, 32 then?
Yeah.
Would that have been the one where you had to do the antiderivative? Okay, so now we're back to this one. Oops. Okay, so 32, so we're back to this one here. And we want the antiderivative of that. Well, what's the antiderivative of cosine? Sine or negative?
No, positive sign. Because
It's positive sine, right? Because the derivative of sine is cosine. So the antiderivative of cosine has to be sine. And we know that the insides always stay the same, so we know that the 2x has to stay in there. Now again, here's where we would test this. We'd say, okay, if I do the derivative of sine, that'd be cosine 2x, but I'd have to kick out a 2, and there's no 2 there. So there must have been a 1/2 sitting here. There must have been a 1/2 sitting there, so that when I did the derivative, which was cosine 2x, kick out a 2, the 2 and the 1/2 would cancel. And then don't forget plus c. Now I know we hadn't talked, we did just very briefly one day, when we first were doing the power rule, we talked a little bit about this too here, but I wasn't sure anybody would remember that. But so that's what's going on with those. Okay? And how that antiderivative, you got to kind of think in reverse. But you always can check. That's the key. If you know the derivative rules, you should be good. You kind of guess, an educated guess of what you think would have been there, and then do the derivative and see if it gets back there. And if it doesn't, then make your adjustments to it, like put on the 1/2. Okay? All right. So that was a big part of what I wanted you to get done there. And now, the last bit, and we have a little bit to talk about in section 5, that 10 through 13. So let's take a look at that. And this is that whole stationary point. This, again, one more time going through this, this whole inflection point, local max min, making number lines, it's very important. So I'm willing to go through it one more time here. And then maybe before our quiz, we'll hit it again. But we've got the video examples and everything else too. And we'll have some more homework examples over the next several days. But it is really important. You know, on the AP test, there's 6 free, half of the AP test is 6 free response questions. And then half of the AP test is like, let's see, what is it, 45 multiple choice questions. So half your score comes from those 45 multiple choice and half your score comes from the 6 free response. And of the 6 free response, usually 2 of them involve max, min, local max, min, global max, min, finding inflection points, stuff from the chart. I mean, that's a big chunk of the AP test. And then, of course, the multiple choice questions have a lot of questions that deal with maxes, mins, and so forth. Okay? So this is a big deal. It's probably the first main thing we've learned that will be in the free response section. The first kind of type of problem you're definitely going to have to be able to do in a free response question on the AP test. So we have this here, and we have our interval -5 to 5. All right, now looking ahead here, they're going to ask me for stationary points, inflection points, local max, local min. So as soon as I hear stationary points, I think what? Derivative equals 0. Inflection points? Second derivative equals 0, right? So right away, as I look ahead at what I'm going to be asked to do, somebody was working in the office the other day on this, and they'd done all their work, and then they got to number 10, and they asked, do I have to do all that work again for 11 and all that work again for 12? No. You could do all that work and then you can answer number 10, answer 11, and you can refer to it, okay? So it all kind of goes together. So that's how I usually start these. So G prime is 1 plus cosine x. Going to set that equal to 0, okay? And I'm going to leave myself a little room, and I'm just going to go right ahead and do G double prime, and that's going to be negative sine x equals 0, right? So I've got to do that. So now, just like we reviewed on the packet, we're going to do what next? Subtract 1. Where does cosine equal negative 1? Where does cosine equal negative 1? At pi. Now you can get that from the unit circle, or you can draw a cosine graph right there at pi. Cosine is negative 1. That is our only stationary point for this particular problem. So that just answered number 10. Okay?
Would negative pi also?
Yes. Yes. Because, oh, thank you. I didn't look at my interval closely enough. Thank you. Did I miss any others? I think if we keep going, it'd have to be at 3 pi, which would be outside the interval. Right. Okay. Yes. So I need those two. All right. This one, where does negative sine equal 0? Well, that's the same place as where sine equals 0, which would be at 0, pi, negative pi. Right? 2 pi is 6.28, so that's outside the window. Okay? Now, is it possible, and what do I label these?
Possible.
Possible inflection points. Okay? Possible inflection points. Is it possible that an inflection point and a stationary, could a point be both? Inflection point and stationary point. Remember the x cubed graph? Right? That's a flat spot. That's a stationary point. The derivative is 0, but also it's a change of inflection there, a change of concavity. Okay? So yeah, that's probably what's going on there. Now, I need to answer question 11, though, I've got to have a number line, and actually to answer 12 and 13. So to answer 11, I'm going to label a G double prime number line. I'm going to put on my 3 possible inflection points, and I'm going to pick points to plug in. And I should pick points that are in my interval. So negative 3 pi halves is in the interval. Negative pi halves is in there. Pi halves. That's why I didn't pick 2 pi, for example, because those are outside the interval, and then something not so nice would have happened. So, and then I got to remember here, because it's negative sine x is my second derivative. So if I put negative 3 pi halves in, here's a sine graph. Negative 3 pi halves is back here at 1. Should actually be a negative 1. Negative pi halves is back here at negative 1, which will turn it positive. Pi halves is 1, which will turn it negative, and then so forth. So I do have inflection points at all 3 of those. Because, and you would have to say, G double prime changes sign. Now we don't have to say positive to negative here, because all we need is a change in concavity. So think about the chart. G double prime changes sign is good enough. So G changes concavity. That's what the chart says. Second derivative changes from positive to negative, or vice versa. Then G changes concavity. So you would have to write that out and then say, instead of possible, say, yes, these are the inflection points. Okay? Guaranteed to have a question like this on the note calculator and on the calculator, where I'm looking for number line, I'm looking for this written out. Got to be there. Okay, that's for points. 12 and 13, local max and min. We're going to want a G prime number line. We're going to put our 2 stationary points on it. We're going to pick some points out here, like negative 3 pi halves, 0, 3 pi halves. We're going to put those back into G prime. Ooh, not at all. So negative 3 pi halves, think about what the cosine graph looks like, or think of the unit circle. Negative 3 pi halves back here at 0, plus 1 is 1. Cosine of 0 is 1, plus 1 is 2. 3 pi halves, cosine of 3 pi halves is 0, plus 1 is 1. So what does that mean? No local max, no local min. Right? Because G prime would have to change from positive to negative to have increasing to decreasing on G. And that's what we thought was going to happen. We said, since we already knew that these were inflection points, you can't have a local max as an inflection point because that doesn't change concavity. Matter of fact, we probably could have said that without doing the number line in this particular instance. We could have said, well, since pi and negative pi are inflection points, they can't be local max and min. Because there would not be concave up or concave down. There's a change in concavity. But this shows it right here. This graph is always increasing because G prime is always positive. So no local max, no local min would be your answer for 12 and 13. Okay? So we went through that 2 days ago. We just kind of hit it pretty hard again. There will be a few extra ones that you'll be allowed to practice and so forth. But that's a big, big part of the next quiz. All right? All right, stand up and stretch for about 30 seconds.
Yes.
Now I'll give you a full minute. Ready? Go. Stand up, move around a little bit, wake up. He'll be back in 45 seconds.
She's hungry.
Really bored.
All right, have a seat. Have a seat. Here we go. That was a minute. There's actual brain research that says if you went longer than a minute, that would actually be counterproductive to what we're trying to do.
I want to see the proof of this.
Well, it's out.
Pull off the article.
Go ahead, Google. All right, here we go. Section. Say I had something like that.
I won't have time to Google.
So we're
Give us too much cover on this one.
somewhere around a minute.
Except for her.
All right.
She's just not cute.
Section 2.5, if you would turn backwards to roughly page 123. Okay? Now, I said the other day that there were, this next quiz, there's kind of two tracks of what the problems are about. Okay, the overall theme is dealing with these functions, the power functions, the exponential functions, and the trig functions, right? And one track was doing the derivative of all those functions, so those were the rules we learned 2 days ago. And then the other part of that track was the chart, the local max, local min, inflection points like we just did. We can do it with power rule equations, we can do it with trig equations, we can do it with exponential. Now, to be honest, we don't do local max and min with exponential very much because they're pretty boring. Exponential graph just goes like this, it's concave up all the time, it doesn't have any inflection points, it doesn't have any local max or mins, right? There's not much to do there. So you don't end up with many local max min problems with exponential and log functions, okay? So with trig functions, though, they're all over the place. We got inflection points, local maxes, mins everywhere. So we tend to gravitate towards those type of problems more for that. So that's one track. Okay, the other track is this thing we're going to learn today called differential equations. All right? And so they're pretty separate. I mean, they both involve derivative, so they do have that in common. But there are some pretty important differential equations that involve exponentials and logs, and that involve the trig functions. And they also involve derivatives, which is what we're doing now. So they kind of go together. But as far as the types of problems you're doing, they're really two kind of separate ideas. Okay, so kind of keep the one track kind of over here, and then what we're doing here now is a little bit different. All right, first of all, definition. A DE, which your book abbreviates DE, okay, a differential equation, is any equation with derivatives in it. Any equation with derivatives in it. So we've actually written some differential equations that you didn't even know. And we didn't call them, but they were differential equations. All right, and the next important thing is lost a pencil. So, need to borrow one? Under your book? All right. A solution, if it's an equation, okay, shh. Listen up here, please. Listen up. If it's an equation, then it's got solution. Okay? So a solution to a differential equation is the original function. We might say y or f, etc., depending what the function was called. Okay, I mean, we could have, the function could be any letter of the alphabet, right, for a name, essentially, but y and f, that's what we use most of the time. Now that's different. We're used to solutions being numbers. Okay, like you solve the equation x equals 2, or that packet we just got to do it, you might have 4 solutions or 8 solutions. But they were numbers, numeric solutions. Because an algebraic equation has numeric solutions. A differential equation has functions as its solution. So that's the first thing you got to kind of get your head around a little bit is it doesn't look like a solution that you're used to seeing. Okay, let's look at a couple of examples. Okay, one example, f prime of x equals 6x plus 5. That's a differential equation. Now, what does something need to be called an equation? An equal sign, right? It's got to have an equal sign. So it's got an equal sign, it's an equation. It's got a derivative in it, it's a differential equation. Okay, that's got a derivative in it, f prime. It's got an equal sign, it's a differential equation. Okay, the solution to this differential equation would be the original function f. What would be the original function f? Three x squared plus 5x plus c. Right? That is the solution to the differential equation. It's the original function f, which we get by doing what you just do there. The antiderivative. Makes sense. If you have f prime, you do the antiderivative, you get f. That's how we solve that differential equation. Okay? Let's look at another one. Y double prime equals negative 9.8. That is a differential equation. It's got a derivative in it, a second derivative actually. Now, you know in equations, polynomial equations, we talk about degree, like a second degree is a quadratic, a third degree is a cubic. In differential equations, they use the word order. This would be a first order differential equation because it's got a first derivative in it. This would be a second order differential equation because it's got a second derivative in it. Not really a big deal. We're mostly work with first and second order differential equations, but that's the term they use. Now, how would we get the original function y as the solution? Well, how are we going to get y? We're going to have to do two antiderivatives, right? We're going to have to first find y prime. What would y prime be? Negative
9.8x
Now, hang on, I'm not going to write X on this one. Now, let's talk about something here. On this one, we don't know what the input variable is. See, on this one we did, because we had the X inside the parentheses, and we saw the X there, so we knew X was the input variable. In this one, because oftentimes we write our derivatives without the input variable there, and we don't know. Many times with differential equations, the input variable is t. And that is because, did anything come to mind when we saw negative 9.8? Gravity, acceleration, gravity. And remember, we did position, velocity, acceleration. Acceleration is the second derivative. Okay, so all I've done here, really all this equation is given me the acceleration equation for gravity. But I put it in terms of position, right? Because position would be y prime would be velocity, y double prime would be acceleration. So when I do the solution to this, I'm really finding what function? No, I just said it. This is acceleration, this one will be velocity, and the next one will be position, right? It goes position, velocity, acceleration. We're going backwards. Acceleration, velocity, then position. Okay? So I'm going to use t. Since this problem is really in kind of disguise, dealing with velocities and acceleration, then usually the input variable is time. So I'm going to put a t there. And then plus c. Right? That would be the velocity equation. Then I keep going. I got to do the antiderivative one more time to get y. What would you get? Well, you'd raise that up to a 2. But then you divide by 2, right? So what's 9.8 divided by 2? Negative 4.9 t squared plus, now we got an interesting dilemma here because this is just a constant. So what should that be? CT plus, now that would be a different constant, so now I'm going to call that C1 and call this one C2. Now, possibly that function looks a little bit familiar. The position function that we used back in chapter 1, or no, maybe it was earlier in chapter 2, said negative 4.9 t squared plus, and then this was the initial velocity, remember that? And then this was the initial height. Well, you think about it, if you come back to the velocity equation, you put a 0 in for t, you would get c as the velocity. So this c right here, which was our c1, is the velocity at time 0, the initial velocity. So sometimes we replace that with a v sub 0 as our constant. But anyway, we got that by solving a differential equation. That's where that equation comes from. So earlier when we worked with that, I said, I'll show you later where that comes from. Here's where it comes from. Started with gravity as a constant, did the antiderivative twice. Okay? All right, the third example, y prime equals 1 over 2y. Okay? What's different about this one? It's got y in it. It's got the output variable in it instead of the input variable. Now keep that, this hasn't been a big deal for us too much, but now it is. We talked about earlier. When we do the derivative or the antiderivative, we do it with respect to the input variable. We did it with respect to x. Here we did it with respect to t. You can't do it with respect to the output variable. It doesn't work. We cannot treat this as a normal do the antiderivative thing. Matter of fact, we don't know what the solution to this is. And we haven't learned enough to be able to find what the solution is. Okay? All right. So, let's organize this into types of differential equations. We're going to encounter 3 types of differential equations. Just like you have linear equations in algebra are easy to solve. Quadratic equations, not quite as easy. You've got to factor, you've got to maybe use a quadratic formula, maybe complete the square. There's a lot of different techniques to use. You get up to cubics and quartics and you may not be able to solve them at all. It gets too complex. Okay? Well, that's what we have with differential equations. So the first type are the first ones we did. Easy to solve. By, well, okay, easy is a comparative term. maybe we should say can be solved by antiderivative, okay? And that would be your example that we just did, f prime equals, what was that example, 6x plus 5? 6x plus 5. Or y double prime equals negative 9.8. You know, all we had to do was just straight antiderivatives. Now, what those looked like, the reason we knew we could do that is we had the input variable, or just a constant, over on the other side. So when you see that, we can just find our solution. Now, and I should back up here a second. What good does it do to give you that solution? Well, once you find that solution, you can then work with it, plug numbers into it, find values, those kind of things. Okay? All right, the second type is one, actually later on there'll be a second one. We're going to memorize the solution. Right? We're not going to know how to solve it, but we are going to memorize the solution. So that one is this one right here. Y prime equals k times y. K is just any constant. Now notice it's got the output variable in it. Now it doesn't have to be y. This could be f prime equals k times f, or p prime equals... A lot of times we do this with populations. And so a lot of times this is p prime equals k times p. Okay? Now why do we do it with populations? Well, because the solution to this is y equals a e to the kt. You might remember the PERT formula from trade class that talks about exponential growth. Right? Well, this is the differential equation that describes that. Now if you think about it, it kind of makes sense. We don't know how in the world this solution came from this, but it kind of makes sense if you think of it in two ways. First of all, if k was a 1, you'd have y prime equals y. Well, what function did we learn about where the slope was equal to the output? E to the x. So it makes sense that it is the e function that we end up with here in the solution, first of all. Second of all, think about this. Think about y being money that you put in the bank. Say y is the amount of money you put in the bank. Then what would the units be on y prime? Dollars per year, let's say. So y would be dollars and y prime would be dollars per year. Well, if you remember from science class, this is called a direct proportion or a direct relationship when you put a k there. This means that the rate of growth of your money, your dollars per year, is going to be proportional to the dollars you put in. The more money you put in the bank, the faster it's going to grow. Right? I mean, that's what exponential growth is. The more money you put in the bank. So this differential equation, this points out the advantage of differential equations. Differential equations very neatly describe the physical situation. Unfortunately, they're not very good to work with numerically. Because if I want to know how much money I have in the bank after 20 years, this equation doesn't do me any good. Because I have nowhere to plug the 20 for the years. This is the equation I need to find how much money I have after 20 years. But this equation describes very nicely what's happening. It says that the rate my money is growing is proportional to the amount I have in there. And the more I put in there, the faster it will grow. So the difference equation has a purpose, and then the solution has a purpose, because the solution is the one we want to work with to find out the information. All right, so you're just going to have to know, and one of your homework problems right off the bat, they give you y prime equals 2y. Right away, when you see that, you have to write down y equals ae to the 2t. Because that k right there is the same as that k right there. And so you go right to that solution, and then you can answer the questions from there. They might give you an initial condition then to plug in, and you'll put in your t in there, you'll put your y there, and you'll be able to find the a. Okay, we'll talk about initial condition here in a second. But that's one of the reasons we worked with these exponential equations and being able to solve the exponential equations, because this one comes out a lot. Exponential growth is a pretty important thing, scientific, pretty important equation. All right, the third type are those that we can't solve, at least yet. Okay? But we could verify a solution or check a solution. For example, let's say I gave you a fourth degree equation and I asked you, is 2 a solution to this? What could you do? Plug in a 2. You plug in a 2 and see if it works. Okay, so if I give you a differential equation that looks like this, y double prime plus 3x equals 4y prime minus 2x squared. That's a differential equation. It's an equation that's got derivatives in it. But we have no way in the world of knowing how to solve that.
Yeah.
But if I said, and let's just do that right now, this is something you want to have in your notes, because this is a problem that will be on the next quiz, where I'll give you a differential equation, and I'll say verify that something is a solution. Okay? So I'm going to ask you this question. Is,
Yeah.
okay, is y equals x to the fourth better? Is y equals x to the fourth a solution? Remember, solutions look like original functions. Is y equals x to the fourth a solution to y double prime plus 3x equals 4y prime minus 2x squared? That is the question. Or I might say verify that y equals x to the fourth is a solution to this differential equation. Okay, now tell me what you told me a minute ago. If I asked you, is 2 a solution, you said what? You'd plug a 2 into the equation. Well, the problem, people get mixed up here, sometimes we actually have 2 equations. Well, what I'm saying is this the solution to this equation? We always plug the solution into the equation. So what we're going to do, and I usually make what I call a T-chart here, because what I'm trying to do, think about what you would do. Think about what you would do if I ask you if, let's take a simple example, 2x plus 3 equals 11. And I ask you if 4 was a solution to that. Well, you wouldn't typically draw in the whole T-chart thing, but these are a little more complex, so it's helpful. But one way to show that is you'd say, okay, well, I'll plug a 4 in for x. That gives me 8 plus 3, which is 11. Yep, checks. I get 11 on both sides, so 4 is a solution. That verified that 4 is a solution right there. That's what I want to do here. So I'm going to put this T-chart thing in here, and I'm going to plug my solution in. So everywhere I see a y, I'm going to put in x to the fourth. Oh, wait, I don't see any y's. So let's do the derivative. What's y prime? 4x to the third. And what's y double prime?
12x squared.
12x squared. So if that's my y, my solution, then y prime would be that, and y double prime would be the other one. So now I'll plug those in. So I'll put 12x squared there. And for the y prime, I'll put 4x cubed. I get 16x cubed minus 2x squared. Are those equal? No. Is there anything I can do algebraically to make them be equal? No. You can't add things across. That's why I put that wall there. To just remind you, this isn't an equation I'm trying to solve. I'm not getting x by itself here. I'm trying to show that the left side is equal to the right side. And clearly, the left side does not equal the right side. So it is not a solution. Notice over here, I did not solve this equation. I took and put a 4 in, worked out the left side to see if the left and right sides were equal. So that is what you do when you're asked to verify a solution. So that's a third type. We got a differential equation we don't know how to solve, but we can verify or check if something is. If it does come out to be a solution, then we can go ahead and work with it in the problem, and that's what will happen in some of the problems that you do. All right. So if you would turn, and we'll start by looking at one of your homework problems here together. And the first part of your homework tonight is 2.5, 3 through 6, 17, 19, 20, and 25. Now, several of these are ones where we're verifying that something is a solution. So let's see which would be a good one. Well, 6 actually would be a really good one. So let's, oh my goodness. It's on the website. All right. So, number 6 says y prime equals negative. Now, it's unfortunate how they wrote that, and that problem is going to come back several times in homework over the next couple days. It's negative 1 over 2y is what they've written there. It's not 1/2 y, it's 1 over 2y. Big difference. Okay? So this is number 6. So in part A, seems like the closer I get to this thing, the worse it is. All right. So in A it says, show that if c is a constant, then y equals square root c minus x is a solution of this differential equation. So in part A, I'm trying to show, they're trying to tell me or convince me that the square root of c minus x is a solution to that. Right? And I need to show that it is. Well, this is this last thing I showed you here. We're going to do this t-chart. So, on the left side, I can go ahead and plug in my y. Right?
C minus x.
C minus x, thank you. C minus x. Okay? So on the right side, I go ahead and put in the y. What am I going to put on the left side? Y prime, which means I got to take the y they gave me and I got to do the derivative. Well, let's see. To do the derivative, it'd sure be a lot easier if we'd write that to the 1/2 power, right? So y prime would be 1/2.
C minus x.
The inside never changes.
To the negative 1/2.
That'll be negative 1/2, and there's one little thing you got to do. Remember when we had that 2 inside the sign that was multiplied by the x, and we said you got to kick out a 2? What's multiplied in here? There's a negative 1 multiplied by the x inside there. We have got to kick out a negative 1, which would make that half, just put a negative on the half. Any number that's multiplied on the inside of a function times the x, we've got to kick that out as that multiplier. All right, so that would be on this side. Negative 1/2 c minus x to the negative 1/2. Now, are those equal?
Yes.
Looking at them, I can see that they're going to be, but you can't stop there. You've got to be able to show that those are equal to where, like my 7th grade daughter, who is really, really smart, but still, she needs to be able to look at that and tell they're equal. Okay, they got to look exactly alike. So, I'm either going to take this negative power and drop that down to the bottom, and then, since it's a 1/2 power, would make it a square root, and do that, so they look the same, or else take this c minus x, make it 1/2 power, bring it up top with the negative power, and do it that way. But you've got to show that the two are alike. So if you have to do some simplifying, you have to do that. Okay? So there you go. In part A, we just verified it. And then in part B, it says, is this also a solution, the negative one? Okay, well, what would have, and then you can go ahead and go through that and see if it happens. Number 8, okay, the next one on there, number 8 says, find the unique solution of the IVP. Okay? The unique solution to the IVP. An IVP is a differential equation. Let's jot this down real quick. IVP is simply a DE plus an IC. There you go. Okay? An initial, it is. An initial value problem is simply another name for a differential equation, but it's got an initial condition thrown in. So when it says solve the initial value problem, they're saying solve the differential equation. Okay? So it would look like this. F prime of x, this is one we've already done, 6x plus 5, right? So to solve that, what do? This would be type 1. Easily solved by an antiderivative. So what do you get? 3x squared plus 5x plus c. Now, if they had not given us the initial condition, we would stop there. We'd say that's the solution to the differential equation. It's a what we call a general solution. But they told us that f of what? No, f of 0 equals negative how much? 3. They told me that f of 0 equals negative 3. So that means I can now plug a 0 in. So I get 0 plus c would have to equal negative 3. Well, c has to equal negative 3. That's an easy one. That's a nice one. They give a 0. So c has to equal negative 3. So my solution then is, and we call that a specific solution then. The solution is that. So an initial value problem just means do your normal thing with your differential equation. If you do the antiderivative, there will always be that plus c when you do an antiderivative, but then you take your initial condition, plug it in, figure out what c is. Okay, so that's a big part of that homework. Now, the other parts are a couple of, listen up now. In the other two sections, the trig exponential, there might be a little bit with differential equations, but I want to throw in a few max-min problems as well so we continue to practice the ones on that track also. So in section 2.6, we'll do 37, 38, and 47. I think one of those is a differential equation type problem. A couple of them have to do, I think, with max-min possible. 2.7 is 39 and 44. Now those take a little longer because those are the, I think 39 is like that local max-min, global max-min kind of thing. So, all right, spend some time with these though. All right, on this next quiz, you have to spend some time getting through the practice of this max-min stuff because they can take some time, and so you're just going to have a lot of time pressure on the quiz if you have to stop and think every time you're doing a step. Okay, so you've got to practice, work your way through the practice on it.
Yeah, we really need to.
Come in and, yeah, I meant to have somebody be the presenter there, but
Well, you could have had me
it didn't work out.
twice.
Are you excited?
No.
What are potato lays?
Oh my
Oh
god.
my god. They're basically
I feel so
little
sorry
tiny
for
hash
you.
browns.
Are those cheesy things that come from the
I promise we'll have some homework time tomorrow.
They're little circle
That's a work time.
hash browns that I'm seasoning on.
They're
They're good.
Yeah.
So, what?
What? Do you live in a hole?
Okay. You need to write down.
You might as well.
Write down these problems, so section 2.5, 2.6, 2.7.
Are we learning that?
Not really.
That just run like
Okay, you will no longer be a Taco Taco person.
like how many times
There.
Don't yell at me.